Hi everyone. I'm Kavya Saxena. I'm a final year PhD student at IIT Kanpur. I'm working with Dr. Vipul Arora, and today I'll be presenting my recent two works based on, that focuses on meta learning based domain adaptation for melody extraction. So the flow of the talk would be somewhat like this. First, I'll be explaining a little concepts of supervised learning, and then what are the different drawbacks of supervised learning, and what are the remedies to solve those problems, and how those remedies can be combined together to solve one problem in the melody extraction field. So if I would start. Okay, so I'll start by supervised learning. What happens in supervised learning is we have a lot of labeled data, right? And if we have a model with parameters theta, so the output would be y hat is equals to, it would be some function of the model with the parameters theta, right? And so in the supervised learning, we can treat any problem as a classification problem or a regression problem, right? So this loss function could either be categorical cross entropy loss or binary cross entropy loss, or it could be a mean squared error loss, right? And to train such a model, we would need input-output pairs. And from the equation one, you can see how the model parameters are being updated using the gradients of the loss function. So, and once the model has been trained in such a way, the trained parameters theta are now used to evaluate on the test data. So this is an end-to-end architecture of a supervised learning model. Now, what happens in, what are the limitations of the supervised learning? So first thing is, to train such a model, we need a lot of data, right? A lot of labeled data. And labeling the data or like obtaining the annotations is a very difficult task. And it's also time consuming. So like first thing is it requires a lot of manual labor, right? And second is we have a lot of scarce data in the sense that the data needs to be, like not all the data is present for the model to be trained, right? So we need to like first scrape the data and obtain the data, and then we need to annotate the data as well. And if we want to automate the process, then for the automation also we'll need a model that has been already trained on a large amount of data, so that the annotations that are generated for the new data, uh, we can obtain that. But then also those annotations might be wrong. We still need some human level intervention to correct those data. So like end-to-end process, it's a very time consuming and labor intensive process. So one of the problems in supervised learning is this. Then second problem is, even though a very large amount of labeled data is available, the model trained on a certain data from a certain domain may not be able to perform very well if we deploy that model into some another domain. So there would be some performance degradation. So these two problems are there for the supervised learning thing. I mean, yeah, it would perform very well if the domain distribution is same. Like the source domain and the target domain distribution, if they are almost same, then the model is able to perform very well. But then if the domains are different, the model will not be able to perform. A very simple example of this could be if a model is trained on some handwritten digits, say MNIST data set. If the model is trained on that data, then it is able to perform very well on a subset of the data, I mean, from the same domain. But if we try to deploy this model on some another domain, for example, if the images are captured using some high quality camera, so that is a different domain. It may or may not be able to perform very well in that particular domain. So these are the two problems that supervised learning it possess. So how do we solve these types of problems? So for the first problem, we can use few-shot learning. And for the second problem, we can use domain adaptation. So the first problem was we need a lot of data. What if a large amount of label data is not present? How do we solve that problem? So that could be solved using few shot learning. And second problem is when the model is not able to perform very well on the target domain. So we can use domain adaptation. So okay. So like as mentioned earlier, few shot learning is it basically overcomes the problem of scarcity of large amount of labeled data. So what we do is we just convert the problem into n way k-short problems, which means n are the number of classes, k are the number of samples per classes. So we can use this type of setting to train the model when the data is very less. And one of the method to solve this type of problem is meta learning. So meta learning is basically, it is of two types. One is metric based and another one is gradient based, which means, okay, so metric based examples are matching networks, prototypical networks, relation networks. So these are already existing networks that are basically used to solve this problem. Uh, I'll not be discussing these in detail because most of my work focuses on the gradient based meta learning. That is model agnostic meta learning algorithm that I used in my work. So what is meta learning? Meta learning is basically a learning to learn algorithm. So it can learn these three types of things. It can learn optimal model initialization, it can learn optimal learning method, and it can learn optimal hyperparameters. So my work was basically focused on optimal model initialization. So in the next few slides, I'll be briefly explaining how meta learning works and then what are the existing, when I'm applying meta learning to my problem or my domain, what are the problems that I faced and how did I find a solution to all these problems. Okay, so it's a two-step process. Meta learning is always a two-step process. So what happens is these are just an abstract definition or the abstract uh, explanation of the algorithm, how it works. Later on, I'll just show the model framework. From there, it will be very clear. So first of all, if we have in meta learning, what happens is you have a number of episodes, right? So episodes can be considered as a single task. So that task can have n way k short kind of structure, which means if I have a model with parameters theta e, right? And y is equals to f, like y is some output of that particular model. And theta e is the model parameters for that particular episodes, which are being initialized with theta naught. Theta naught is the already pre-trained model weights. So if I have to explain it in how this works, is suppose we have a model with parameters theta naught already pre-trained on some of the task, like yeah, on a subset of data from a single domain maybe. So now from the same domain, if I have different classes that the model has not already seen during pre-training. So how can we use these data or in order to train the model with meta learning? So, I mean, these equations might not be clear. This diagram will make it more clear. So this is the meta training framework. So now what happens is we have a meta learner that is theta naught, which is already some pre-trained model or some randomly initialized model with parameters theta naught. So it's a two-step process. One is, these parameters theta naught are used to initialize the parameters theta e. So theta e is just it's just a episode model, which means we have different types of episodes, E1, E2, up, for example, till En, and each episode has n way k short kind of structure. So what happens is this XS and YS is the support set for that particular base learner. So theta E is trained on that particular support set, right? So now these updated parameters theta E will now see the XQ and XQ. XQ is the query set data, right? So when we pass SQ to the base learner, it gives me some prediction y hat q, and from there we calculate the loss, which is used to now update the initial parameter theta naught, right? So what happens is up till this step, up till this step. So what we do is base learner is trained on several episodes, right? And then what we do is we accumulate the loss, calculate, and then we do the final iteration of the theta naught, like final updation of the meta-learner model. So in short, what we do is we have one second, next slide. I'll just show this. So training the base learner is called the inner loop optimization, and training the meta learner is called the outer loop optimization. So what happens is for each episode, we have n number of inner loop optimizations, and then after the n number of inner loop optimizations happening for each of the episodes, those losses are accumulated, and then we have a final updation or a single updation of the learner that happens in the outer loop optimization. So this is what the meta learning framework looks like. So if you have any questions till now, you can ask. Yeah.
Can you explain the difference between the, I guess it's the source data and carry data?
Sure. Okay. So what happens is you can okay, for a particular episode, if we have NP K-short type of data points, okay, so we have n classes. Suppose we have 5 classes, right? And we have one example per class. So this is a 5-way one-shot problem. Okay. Now this architecture, this particular data configuration is used to train the base learner, and that is the XS and YS, right? The support set data. Now the query data is the same classes, the same 5 classes, but a different sample from that particular class. Okay, but this XQ is not seen by the model. This is okay. So you can think it in this way that model for a particular episode, we are training some model and then we are testing it on some test data from the same classes. Okay, and is it clear?
And the loss is only computed using the support data?
No, so loss is calculated by using the query data.
Okay.
So it's just like if for a moment, if you forget this theta naught, and if you just focus on this particular structure, the inner loop and outer loop optimization structure. So what happens is you have this label data, right? XS and YS is the label data, N-way, K-short data. So you train the model here, and after training, you have some like updated parameters here. Now, this updated parameters, we will just give some query data as a test data here. So if we give this test data, here we calculate the loss on the query set itself. So now this, up till this point, it we perform this particular like architecture or the procedure for every episode. So at this, after n episodes, we have n losses, right? So this meta learner now is updated by the cumulative loss from all the episodes. So like this happens for every episode, and meta learner is updated only once after it has seen all the episodes, right? Yeah.
So for the output optimization, we basically freeze the base learner and then get the loss.
So can you?
Yeah, so, in optimization, you can take the way for a day, then you freeze the model, so you don't change the parameters. So the query data are passed through the model without changing the parameters, you just update the loss and
Yeah.
then update.
Yeah. Right. Should I move forward? Yeah, okay. So this is the algorithm for meta training, right? So what we have different tasks and we have learning rates. Okay, so like we have two learning rates because we need one learning rate for the inner loop optimization and one rate for the outer loop optimization, right? So what we do is first we initialize theta e with theta naught. So theta naught is some pre-trained model, right? So first we initialize theta e with theta naught. Then what we do is for all episodes e, what we do, we divide e into support set and query set, right? Update theta e on the support set with the recent algorithm. And then we have this theta e for every episode, right? From this theta e, some mistake here. Okay, so this theta e is obtained for every episode. Okay, now after the model has seen all the episodes, we update the meta learner theta naught with the cumulative loss functions. Cumulative loss update from all the episodes. So this is the meta training algorithm as it is. Now, any guesses on what the learning rates like should be? If I assume alpha is the learning rate for inner loop optimization and beta is the learning rate for outer loop optimization, then should alpha be less than beta or the other way around? Or do you think it should be?
Can you guys again the question?
Okay, so like if alpha is the learning rate for inner loop optimization and beta is the learning rate for the outer loop optimization, so should alpha be less than beta or the other way around?
This was related to that alpha should be smaller.
Alpha should be smaller than beta, you are saying. Okay. Any other guesses? I mean, any other would be like beta is greater than alpha is greater than.
So it depends on the amount of data you have, because you are training on the cumulative loss. So if you have the cumulative loss with a very high rate, then obviously you will pretty much not compare to something slow. Yes, alpha should be similar to beta.
Okay, so you're saying alpha should be smaller than. Okay, what about if we think this in a way that theta, okay, so now we are trying our model to learn different types of tasks, right? So we don't want model to just like it should not, the parameters should not be updated with a lot of large amount of gradient, right? So because if I say my pre-trained model is trained on some source domain data, and now I'm training model in such a way that it should learn the new data like from the very few samples, and it should also not forget the things that it has already learned. So alpha can be greater than beta, but beta should definitely be like very less, because we don't want our model to just like forget whatever it has learned previously, right? Beta naught is already a pre-trained model. If my beta is very large, then it may or may not forget whatever it has learned, right? So alpha should be greater than equals to beta, like we can say like that.
Can I understand this, for example, the inner loop is a warm up for the outer loop, and you can use a pretty big alpha to make the current model adapt to that task. And then you compute the loss in the outer loop, and then you kind of update the model.
I mean, yeah, it's kind of, so what happens in normal supervised learning is, whenever you're training the model, it's always, the loss is always calculated on the training data, right? In a normal supervised learning end-to-end architecture. But here, uh, the slight difference is, we are training the model in such a way that the loss is not calculated on the training data, it's calculated on the test data. So it's like a double step learning thing, right? So we can understand this in such a way that, I mean, yeah, what you said partly is correct. Like, we can assume this particular architecture uh, in such a way that it basically is trying to learn or adapt to a very few data points without forgetting the already trained points it has been like trained on, right? I mean, is it? So this is what the architecture of our normal meta training model looks like. One prerequisite for such a training is it only works well when it's like NVK short kind of thing, okay, right? Because we have fixed number of classes. Suppose we have 5 classes, and for each of the 5 classes, we have 5 samples, for example. So in that case, it works very good. But what about uh, oh, okay. So that problem I'll just discuss after this fine tuning part. So yeah, so the previous thing that we discussed was how can we like that was a solution to our first problem where we do not have a large amount of labeled data, right? And second is even though we have large amount of labeled data, it is not able to perform very well on the target domain. So like very normal and very basic method is fine tuning. We just freeze the feature extractor layers, and then we fine tune on the classifier layer to just uh, adapt the model on that particular data set. So we have a large number of, I mean, we have large networks that are trained on the large amount of labeled data sets. And so now if I want to apply this model on some of the downstream tasks that I have, what I'll do, I'll just train the model, like I'll reach the second step, right? And then I have a large model with pre-trained, I mean, I have a large model that is trained on the large amount of labeled data set. Now from third point, I'll just discard the classifier layer, and then I'll use that, I'll replace that by phi dash, which is which is the classifier layer according to my downstream task. And then I just, and I freeze the feature structure layer and update the model. So this is how normal fine tuning works, and it works very well in like, I mean, when the data is not very, I mean, when the data distribution does not vary much. So it works like very well in that particular scenario. Now, when we have these two things, now, if I want to apply fine tuning or meta learning in my domain, that is melody extraction, so I face a number of problems. One of the problem is when I'm trying to apply meta learning in melody extraction, we saw that meta learning works very well when we have NVK short kind of problem statement. But what happens in melody is we have we don't have like samples for every class, right? Because in melody we have vocals ranging from some frequency to some other frequency. For example, from 51 hertz to some 830 hertz, right? And we divide this frequency range into discretized bits. So it is not, I mean, we are not very sure whether we get the same number of samples for each of the frequency bits. Okay. So, I mean, audios are of two types, monophonic and polyphonic. Monophonic is like we have at a time only one instrument or one source is present. Polyphonic is, I mean, at least one of the sources present at any of the time. So when we treat melody extraction as a classification problem, it creates class imbalance. And this class imbalance can be shown in this particular plot, if you can see. So the standard data sets that are used in melody extractions are MIR1K, ADC 2004, and MIREX 05. So x-axis are the number of pitch classes, and the pitch ranges from 51.91 hertz to 18.51 hertz. So now this particular range has been discretized in like one, and the bins are at 1/8 the semitones. So once we have these kind of these kind of classes, so you can see from the plots that there is a lot of like variation. It's a there is a lot of class imbalance present. Also, the plots are only for the voiced range. So when we consider the unvoiced frames, then the proportion is very high. So I have not plotted that here at the zeroth pitch class. Zeroth pitch class represents the unvoiced class. So the proportion would be very high. So just to make it look like normal, so I have not plotted that, but you can see there is a lot of class variation even in the voiced frame. So if I train my model on MIR1K dataset and then test it on ADC and MIREX 05, the performance will degrade, right? Now, if I want my model to perform very well on the other two datasets also, then how can we obtain that? So this is what I have tried to cater to by using meta learning. So this meta learning based source domain adaptation is the paper that has been accepted in MNSP 2004. So okay, I have two of the source domains, right? I mean, not exactly two domains, but the same domain divided into two parts. So D1S is the label data. I considered MIR1K as the source domain, and that domain has been divided into D1S and DS2. Okay. So my model has been normally pre-trained on DS1 dataset, and this DS2 dataset is being considered for the meta learning part, right? Target domain is, these target domains are the ADC and the MIREX 05 data. So, and we have a very few, for example, we have very few examples of, or the labeled examples in the target domain, right? Such that K is very less than J. So the number of labeled samples in the target domain is very less than number of labeled samples present in the source domain, right? So how do we basically adapt to such a domain where the samples are very less? So, okay, so now what I'll do is, okay, this is normal pre-training. We have a spectrogram, we have the feature extractor layer theta, and then we have a classifier phi. So this model has been trained end-to-end on D1S dataset, right? Now what we do is we just freeze theta, that is the feature extractor layers, parameters, and then only phi is being updated in the subsequent training, right? So as I mentioned in the normal meta learning slide, that we have a support set where NBK short kind of data structure is present, right? Which means you have like you have K samples for every N of the N classes present, right? And also in the query set, you have samples corresponding to those N classes, at least one sample corresponding to all the classes present. But that is not the case here in the audio, like in the audio domain, because every frame of the spectrogram may or may not be having like So every frame of the spectrogram is classified into one of the classes, right? So there is a very high possibility that one of the frames may not be classified into any of the classes that are present in the source domain and that are present in the like the query, sorry, the uh, target domain as well. So what I mean to say is, okay, so each episode B is it consists of a support set that is a subset of the D2S data set, right? And a query set TPQ defined as the single input output pair. So what happens is, if I have, okay, we can explain this in such a way that I have a single audio in the target domain, which is labeled, right? I mean, that means every frame of the spectrogram has been assigned to some of the frequency, and that information I have, right? So that acts as a query set now. The query set in the initial meta learning framework consists of samples, like at least one sample from all the n classes, right? Here the number of classes are not, the number of classes are fixed, but the number of samples per class is not fixed, right? So there is a class imbalance in the query set as well, and then there is a class imbalance in the support set as well, right? So how do I basically cater to this type of like architecture? So like, is there any question or in how we have created these type of support and query data set? Otherwise, the subsequent slides, I mean, there would be a difficulty in understanding subsequent. Any questions? Okay. So, yeah. So now there's a very high class imbalance in the support set as well as in the query set. So what I do is I just train. So yeah. So now this is how the model has been trained using meta learning, right? So this file here is the initial pre-trained classifier, right? Now this classifier is used to initialize the theta b, which is the parameters at each episode. For each episode, we calculate from the support set, we train the model theta b, right? The parameters, and we do n number of iterations. So my parameters now become theta b n after n number of trainings, right? Now when this happens, now I give my this XBQ is the spectrogram from the query domain. So my model has been trained on the support domain. My model is now being tested on the query domain, and it is calculating the loss, right? So after it has seen all the episodes, it calculates the loss for each of the episodes, right, on the queries. So now my initial model or the initial classifier is now updated using this loss, the cumulative loss, and this is how one iteration of the meta training of the melody extraction problem happens, right? But still the problem of that class imbalance remains. So to cater to that, so now loss is calculated in this way, right? Loss is calculated in this way, and obviously it's a weighted categorical cross entropy loss because there's a lot of class imbalance. But then this weights have been calculated in such a way, which means, okay, now this equation is important because this equation is important because this will cater to the class imbalance present in the support as well as in the query set. So what happens is WCS is the weights of the classes present in the support set. I mean, each frame of the spectrogram is classified into one of the classes, right? So WS is just, WCS is calculated as the inverse of the frequency of all the samples corresponding to that particular class, right? And WCQ is it's a similar kind of weight, but calculated for the spectrogram in the queries. Okay, and this beta C is some scaling factor, which was I have mentioned it. Like basically the value was 0.01 something. Like it's a very small value, beta C. Yeah, I'll just verify how. it was calculated by some formula. So in this way, the weights has been calculated. Now the loss that is, the query loss that is calculated in the previous slide. This loss on the query set has been calculated by using the categorical cross entropy loss by using the weights calculated in equation number 3. So when we calculate like this, so it caters to both of the both class imbalance in the source, in the support set as well as query set. In one line, we can say that my model should not be biased towards the classes that are present in the support set, but are not present in the query set. It should be able to learn the difference if one sample, if one sample is present in the support set, one sample per class is present in a support set, then the model may not be able to perform very well or may not be able to predict if that particular class is present in the query set because it has seen only one sample in the support set, right? So in order to maintain that balance, we use equation number 3, and the weights calculated in such a way that caters to a balance between the classes present in the support as well as in the query set. So this is how this particular meta learning works this works in in extracting melody from the from the target domain. So this would basically mean that when we have a very small amount of label data in the target domain, my model is able to learn the difference, and the model is able to adapt to the target domain, and then it can perform very well on the rest of the test data, unlabeled data. So the performance basically that we obtained here is. So this is basically the comparison of the different domain adaptation techniques. So this is the fine-tuning very basic algorithm. When we use fine-tuning, then so these ADC and MARIX are the target domains, and I have basically so I've compared fine-tuning, and MAML is the original meta-learning algorithm, where it does not cater to any class imbalance sort of thing. So when we do this is the performance is 83.55%. RPA. And this is the third row is R method, and you can see the difference. Even if we have very few labeled samples in the target domain, it is able to very well adapt to that particular domain. So this is how the comparison of different domain adaptation algorithms look like. Any question up till now? So, okay, so this is one of the works that I did, and actually this is my initial work that should ideally have been published before my next work, but yeah, it got rejected, so that's it. So this is this work caters to when we have very few label samples from the target domain and how my model is very well able to adapt to that domain. So now if I extend this problem statement in such a way that okay, so this current work is on the audio level, like it's on the entire spectrogram, right? Suppose I have 5 seconds of audio. So 5 seconds audio in the support set and 5 seconds audio in the query set, right? Now, what if I have to just break this down further and then perform these set of experiments on the frame level, like frame level, which means now my entire spectrogram is divided into query and support set. It's the single spectrogram that is being divided into support and query set, right? In the current like framework, I have two separate spectrograms, one in the support set and one in the query set. Support set spectrogram is related to the source domain, and query set spectrogram is related to the target domain. This is the current architecture. Now, what I did was, so like few of the things are very common in the like common from the previous method. Like we do pre-training pre-training on the D1S data set. This is common. Now what we have done is we have modified the meta training step. How? Okay. Now this particular work basically, okay, now if I want to see where my model is not able to perform very well, like where the confidence of the model is less. So I should consider only those points, right? Like in the previous work, we have randomly selected, like we have already predefined, like two samples from the target domain are labeled, right? And we don't have that liberty of we don't have that we have not given that liberty to the model to give those points that give those points on which the model is least confident, right? So in this work, what I did, I extended the previous work in such a way that now my model is able to give me the least confident frames as well. So I basically kind of incorporated active learning into this so that only those frames can be, I mean, the model can be trained on those frames where the confidence is very less, so that it can improve the overall performance of melody extraction as well. So the very basic confidence criteria, as everybody knows, is the maximum class probability, right? So we have, suppose we have 5 classes, and if we give some input X, and the X is being, and that input is being classified into one of the classes, right? So how do we calculate that which on to which class it has been classified? We just see the maximum class probability, right? We do argmax and we see the maximum class probability, but that probability may or may not be true, right? So, which means if the performance is, if the prediction is wrong, then also that probability is very high. If the prediction is correct, then also that probability is very high, right? Which would mean if I have, for example, for a particular image, I have ground truth as class 2, okay? And in the prediction, highest probability is given to class 2, then it means the prediction is correct, right? If the highest probability is given to class 3, then the prediction is class 3, but the prediction is wrong, right? So the wrong prediction has also been given a high probability, and the correct prediction has also been given a high probability. So this is not a very good criteria to calculate the confidence, right? Now, better criteria is the normalized true class probability. So this would mean, can I use the board?
So we also turn on the camera.
Yeah, in that case, you have my phone on the camera.
Okay. So which would mean if I have this X and I have some model phi, and it has been classified into,
He also do the clearing with camera as well because they're
okay, how to like,
You what?
remove the.
Blurry. Yeah. Let me check.
So if this particular image has been classified into these classes, and if I say my 3, 6, 8. Right, it sums up to 1. Yeah, okay. So now if this particular X has been these are the probability values corresponding to these classes. So this would mean this has the highest probability, which means the prediction is class 2, right? Y hat is class 2. My Y was initially class 0. So this is clearly a very wrong prediction, but the probability associated with this prediction is 0.6, which is not correct. I mean, this should be pretty less because the prediction is wrong. So what I do is we consider the true class probability, which means I know that because this is supervised learning, I know the ground truth, right? So Y is, I mean, the actual ground truth is 0. And now I will check this particular probability value. So this is the true class probability. This is the maximum class probability, right? So if we check the true class probability, it's 0.1, which is kind of an indicator that since the prediction is wrong, the probability is very less. So this is a better criteria to consider. I mean, better confidence criteria to consider, right? But then if I do the normalized true class probability, this would be in the range 0 to 1. So that is what I have considered. So I've considered the normalized true class probability as the confidence criteria, just to ensure, I mean, this is the confidence criteria that I have considered. So like any doubts still, yeah.
If you have an equal probable outcome, so everything is the same. So you have 1 over the normalized true class probability, and this result in a problem. So in active learning, we do have other criteria to try to measure the top 2 difference or get the histogram or see how far it is from the uniform distribution.
Okay.
So you check that.
So like, if I've understood your question correctly, you're saying that this type of setting would create a problem. Like
Yeah.
what kind of
So
problem?
if everything is set to problem, so right now you have.
If
0.2.
everything is equal problem, then that would not sum up to 1, right? Like this is the starts.
1 divided by 5, so it's 0.2. Yeah,
So this is the,
something very, or at least the difference can be very small. So let's say the first one has 0.21 and the other one has 0.19 and everything else has 0.2.
okay,
Right.
yeah, in that way. Okay, so that is a very good point that you have mentioned. So these type of so I basically, that depends upon the how well trained your pre-trained model is, right? If your pre-trained model is performing very well or as the classification task, so then the difference that you have mentioned, like 0.21 and 0.19, there would be very rare cases of these happening, because I checked it, like in my problem statement, these were very few instances like this present. So in this case, some overlap would be there, like, oh, some overlap would be there.
No, I understood.
Yeah. So, yeah, that this is true, but then in my case, these instances are very less. So this is how I calculated the normalized true class probability. Now what I did is, but if I want to deploy this in the target domain, then I don't have the ground truth, right? So this true class probability, how can we calculate? So we train an additional, okay, so this is the plot that different confidence criterias happen. So this first one is the maximum class probability. You can see the incorrect predictions are also getting like high confidence, which is very long. So this is the true class probability. And this region here is the overlap that you mentioned. So this overlap is very less in my case, because I am considering only the least confident points. I'm training on the very least confident, not on the not on the points where the model is confused, right? So this region is where the model is confused, right? Near 0.5 probability area. So, and this is the normalized TCP ground truth, and this is the output of what I have trained my, how I have trained my confidence model, which means I'll just show this particular like this, okay? So like each, okay, so this is for a particular frame number 5. So we have some true class probability, C star M for that particular frame. And we train the confidence model by using mean squared error loss, normal mean squared error loss, because the ground truth will not be present in the target domain, right? In the domain that we need to test our model. So the confidence model is being trained in such a way using the mean squared error loss. Now, once we have the pre-trained model and the pre-trained confidence model, now we will apply meta learning like this. Okay. So what happens is here we consider each spectrogram as an episode. Okay. So here we do not consider a bunch of spectrograms as an episode. A single audio is considered as an episode. So when this audio is given as an input to the classifier, sorry, the feature extractor, and then through the classifier, it will give me some prediction, right? From theta b, I get like y hat b is the prediction of the melody contour of the spectrogram. From phi b model, that is the confidence model for that particular episode, I get the confidence values at each frame, right? I'll select those frames where the confidence is very low. Now, those frames act as the support set for that particular episode. So I train my model on those frames. And then once I have trained my model on those frames, I'll just use the rest of the frames as the query set to to predict the melody contour on the query frames. So now from this, I calculate the loss, right? I calculate the loss on the query set, itself. So this is just to ensure that even though the model is not confident on few of the frames, if I do meta learning in such a way that if I train the model on support set and then test it on the query set, the model should be able to learn the least confident frames while retaining the performance on the query set. So this is how I have trained my model in the source domain. So this part is called the active meta training part. Now, if I have to deploy this into the target domain, here, since I don't know the true class probability because the audios are unlabeled. So here is where this confidence model comes into play. So the similar thing happens here. I mean, the spectrogram in the target domain is given as an input. The y hat b is the prediction of the model, and then the c hat b is the confidence at each frames. Wherever I have the low confidence frames, the model is being trained on the support set, and then I get the prediction of the entire I get the prediction on the query set, right? So by doing this, it is getting adapted to few of the frames in the target domain, and still it is able to perform very well in extracting the pitch of the entire audio. So this could be very well used as an application in annotating the data, right? Now, annotation, like annotation of pitches or the melody contour in polyphonic audio is a very like tiring and very labor intensive task. So this could very well like to a certain extent it can automate or it can reduce the amount of human labor used to annotate the data. So I did like create a tool for this. So it's like almost about to be get completed. I have to submit that. I mean, that is an ongoing work. I have to submit that in the paper. But yeah, so if I have given that tool to the annotators present in our lab, and they are finding it to be very useful in the sense that their manual effort has been reduced, significantly reduced. So this is the entire framework that I did, and this work was like published in TSLP. So this is the performance metric. This HAR dataset is the dataset that we released, I mean, in the TSLP paper, Hindustani Alankar. So basically, we wanted to check the performance of this domain adaptation thing in various domains. So ADC and Myrex are this, I think, English datasets, and this was the Hindustani classical dataset. So, I mean, it's an Indian classical dataset. So I did various experiments, and you can see the AML, I mean, this is active meta learning, R method is able to perform very well as compared to other adaptive algorithms. So, okay, so random adaptation and active adaptation, there are two things. Active adaptation is the one that I have done, where the confidence model is able to give me some, I mean, is able to give me the least confident frames, right? Random adaptation is the model is randomly choosing the points to adapt on. Suppose if I fix, like my model needs to adapt on 10 frames. So it's randomly choosing 10 frames and it is adapting on. So random adaptation obviously would perform, so yeah, I mean, okay, this is both MAMM, right? So even if it was random adaptation or active adaptation, the initial original MAML, there was no significant difference in the original MAML model. But when we did this, our method, the performance significantly improved. And not only to the like one or two data sets, it also did very well on the Hindustani classical data set. So the tool that I built based on this was to annotate the Hindustani classical data set because we wanted to generate more data from our lab. So that's why it was able to do well. So yeah, any questions? Any questions?
No, there are no questions on that.
Thank you for your talk. Are there any questions online at the moment?
Can I ask something?
Sorry?
Can I ask something?
Yeah, sure.
So can we go back to the distribution that you have?
This one?
No, distribution. So you have 4 plots with the distribution of.
Oh,
correct and
okay, the
correct.
plots. This one?
Yes, so the confidence right now for the correct and incorrect are based on your true, the
Yeah,
ratio between the true class probability. And
yeah.
did you try to calculate the entropy of the incorrect and the correct ones?
No, I did not try that.
Because I think it showcase what I'm trying to say right now. It's
Mhm.
basically, it depends on the definition of what is incorrect right now on this case, right? For me, the incorrect one not only be something that has a high probability on the incorrect class, but something that has equal probabilities in multiple ones and still incorrect. So there are some
Yeah,
other cases
okay.
that I don't know if this.
Yeah, yeah, I can, yeah, I'll look into that
I guess
definitely.
it's okay. But the incorrect also fall into a high entropy. So it's.
Still a couple of more general questions. Firstly, thanks for your talks. Very nice explanations. Yeah, what has been your experience in general with training mammal and your adapted variants in terms of hyperparameter optimization and like how many inner adaptations you should have, or so I found it very sensitive in general, and I'm sure it depends on maybe it depends on the domain, and maybe you have some intuition on that as well, like
Yeah.
depending on how far the domain is, what kind of changes you found yourself needed to do.
Okay, so like this meta learning algorithm has mostly been used in image domain, right? From the paper that I read, that the initial paper, model agnostic paper, I think by Chelsea Penn. So that paper and subsequent papers, I found out that the inner loop the number of iterations in the inner loop optimizations were very huge. Like the number of iterations were very large. I think 10,000 iterations per episode in the inner loop optimization. But that depends on the problem statement. Like I did a bunch of experiments by changing just these hyperparameters. So in audio domain, the number of iterations in the inner loop was the bottleneck that I faced, because I so like the model that I was using and the data itself, the spectrogram, I used like 3 seconds to 5 seconds spectrogram. So data is not that large, but yeah, I mean, because I was calculating it was a spectrogram, right? So the feature extraction part was intensive. Then, I mean, what I found the problem was my model was not able to converge, or like if I did 10 iterations, the model was not able to converge properly. But then if I did 15 iterations, the model was like it was overfitting. So I mean the loss was not reducing, it got overfitted. So it usually depends on the problem statement that you're working on. So I did a lot of experiments just tuning the hyperparameters. One thing is also the learning rate that I tried. I mean, I saw a significant deviation in the performance even while changing the learning rate a little bit. So, I mean, the model was not able to perform very well if I just increase the learning rate by 0.5. I mean, like into 0.5 times. So, yeah, these two things are the only things that I needed to take care of while training the meta learning model. But then, yes, the end-to-end architecture was itself very. I mean, this type of thing in audio domain is very new. Like nobody has done on the frame level kind of stuff. So yeah, I did face some problem in like formalizing the problem and then tuning the hyperparameters. So I mean, if you are trying in audio domain, so you can look into the learning rates as well as the number of inner loop optimizations according to your problem statement.
I guess, I mean, following up with this from the continual learning side, it's like recently been identified as a sort of stability gap of when an addition usually happens on the more form strokes. And that feels like a very interesting area to explore if you can somehow quantify the distance of between like your base and adaptation set. So if it's close enough, it seems like it will still be useful, but I'm guessing for a static data set, maybe a bit more of a gap. In a sort of intermediate state, it seems like it's more of a problem sort of parameters choose for the position. I guess it's try.
Yeah, I mean, this is,
Stuff.
yeah. So like these hyperparameters are sometimes the bottleneck. I mean, you need to really do a lot of experiments just to understand how the things work. So yeah, this took me a lot of time, like because I did a lot of experiments in understanding how the gradients were how the gradients were changing with changing the learning rate. And after I think 10-15 experiments, I got to find out the correct, I mean, from,
So that's great.
yeah,
Please let me know if-
sorry.
Do you have the happy number stuff?
Yeah, that is in the paper, yeah. So, yeah, I have, I think. Okay, so there is some, I have, linked paper in some of the, I mean, in the footnote, yeah, this here. So I can share the presentation, you can have a look.
There's the question that's,
Thank you.